Hello, so today we'll be going over and creating the basic functions necessary for a binary search tree in the Racket language. Here we go. First, we need to define our language. In this case, we're going to be using standard Racket. Nothing exciting there. And let's do a basic print just to make sure everything is running, right? So we'll start off. We'll just print my normal starting string. Let's see if this works. We'll save it. And in my terminal down here, we will run Racket on BST Racket. And we're starting. So we have something running. So let's begin. First, we'll add a comment, right? What data structure will we use for a binary search tree? We will pretty much use the standard. Classically, we will use a list with 3 elements. All right. Those elements, right, we will be, what's in a tree? Well, trees are built with nodes. I'm not going to go too much into trees. You can research that, but trees are built of nodes, and so what is in a node, right? Node is a value and sub-trees. Because this is a binary search tree, there is an ordering to those trees, and there is a specific number of them. What are those? We will have 2 subtrees. We will call them left and right. And left and right will be an ordering based on the ordered value, some sort of signifier, some sort of ordering, and all the nodes on the left will be less than, and all the nodes on the right will be greater, right? So nodes are ordered, and nodes on the left are less than the current or parent node. All right. So again, go research the basic structure of a binary search tree. I want to mostly here get to just the implementation. So what function should we start with? All right. We should probably start with creating what is and how would we create an initial, clicking around, an initial binary search tree, right? New. So define, and we will have a couple of them. So new, and what does it take? Just like we mentioned, it takes a value, which in this case might have a default of empty essentially, or none. There is no value. Here we'll use an empty list, and remember, and then the left and right subtrees, right? We will also need, and they also start out as empty. All right, so we have our initial definition, and because this is a match, we will need a couple matches. And why do we need a couple matches? Well, ultimately, the very first one is if we don't even give a value, a user has just asked for an empty or an initial tree to operate on, then the default value will be used, and we don't care what left and right was sent. And what is a new but a tree without any actual content? It's an empty list, right? Perfect. Otherwise, we have our matches just go through, and we have our value left and right, whatever those may actually be. And so now we need to create our list of, as we said, our values in our subtrees. And because we're calling left and right, here we will do a little bit of ordering to get the to keep the idea in our heads of a tree is a value with its 2 left and right subtrees. So we have left, the value that the user came in, and right. So let's format this, and now we have a tree. Let's save this and run it, even if nothing actually happens. We don't seem to have any errors, so let's keep going. Excellent. What do we need now? Well, we probably should identify how, if we have a empty binary search tree. And I had already forgotten. I want to preface all my functions with BST. So BST new. So BST empty, and in this case, because it's a list, we can just reuse the list predicate in Racket. That's lovely. And then we'll want to be able to get different aspects of the different parts of a node, right? What parts might we want? Well, we probably want the value. And how do we get the value? Well, we know it's the second element. In Racket, we have a predefined function called second, which gives us the second value in the list. So we're going to use that. So that's all lovely and good. And then what else do we need? Well, we could get left and right, and that makes a lot of sense. Or we could also just get all of the children. So, you know, for the moment, I'm going to create a function that just gives us all of the children. And so we have BST children for this particular tree. And what are the children? Well, the children are a list of the first item from the tree and give us a little space. The third item from the tree, right? Because those are a node is 3 elements. So if we run this, any change, any different? No, we're still running and we're all good. Now what do we need to do? We need to actually be able to populate a tree. And so we usually call that add. So we're going to be able to add to a tree a value to a tree. All right? This is also another match. So what might our trees, what type of tree might we be given? We might be given an empty tree. So if we're given an empty tree and a value, what do we do? Well, it's nice and easy. We actually just call our new with just that value, right? We have no left and rights. And so we can just call BST new with our value. It'll do the matching up above. It'll put in a value, and left and right will be empty. So that's great. That's all nice and easy. And the other case is when whatever the value is, and that's lovely, and then we get a tree, and again a tree has 3 elements, has a left, the tree itself has a value, and then it has a right, right? So that's awesome. We've got that we've done our pattern matching, and we pulled out the left and right subtrees and the tree value. Now we need to do something with them. And this is where our ordering comes in. We'll do this quickly. We'll do a cond statement. And one of the conditions is what? Well, if the value is less than the tree's value, what do? We need to insert this into the left subtree. So what does that look like? We're going to create a new node, a new tree, where we're creating the new and we send in the tree value. So we keep this node's value. And then the left is BST add. We're going to add this value into the left tree. And we're going to continue with the right tree. All right. So what are we doing here? Again, if the value to be inserted is less than the current node, then we want to insert it into the left tree and keep this particular node's value. Otherwise, we want the other case, so we'll just duplicate this. What is the other case? It's when the tree value is less than the value, and so therefore we're going to build a node that still has the tree value, but instead of adding into the left, we're going to add it into the right. Oops, a little bit zealous on the delete. And then we have our final case, right? Our case where if our node is if the two values are identical, for the moment, we're not going to allow duplicates. All right, so excellent. It's a little hard to see. I'll resize a few things a bit, just so that we don't have to see so much. Awesome. So if we run this, we haven't really done anything. We're still starting, but there does not seem to be any errors. So this is great. We can now add stuff, so we should probably do a bit of testing. All right, so let's test it out. Test the creation and addition of values to a binary search tree. So we need some data. Fine. What should we get? How about some numbers? What numbers should we get? How about we get from 0 to 4? We'll have 5 values, right? Nice and simple. Let's print this out so that we can see these things. Our nums are numbers. We will save this, and let's run it. Now we should actually see some different output. We have our numbers 0 through 3, but I actually want 5 numbers. I should have done the range. I always forget. This is lovely. So we've now got 4. Perfect. So now we need to add this into, we need to build out a tree. All right. So let's define our first tree, 1, and how are we going to do this? What is a useful function at this point? It's probably we want to insert each of these. So it's a fold. And we're going to fold over some procedure. What are we doing? We're going to fold each element into what? A tree. What are we going to do? We're going to add into a tree the numbers, right? So we are adding into a new tree each number one at a time, and because this is a reduce or a fold, in theory, this should build out our tree through a series of calls with an accumulator and a value. So now let's display this. Let's say, let's just call this the tree. See what it looks like. Tree 1. All right. We'll save it, and if we run it, what do we see? 0 comes in first. 0, the next number is 1. It's not going to go to the left, right, because it's greater. It's going to go to the right. 2 comes in. It's going to go to the right of the 1. 3 comes in, and on and on. So this is a right-leaning tree. So it looks like it's working. Right? So perfect. So what should we try now? Well, we can try this, but reversed. Right? Let's make sure we can build out a left-leaning tree. All right. So how might we do that? Well, we can, instead of our tree 1 here, and instead of saving this off, what we can do is we can do our same fold. We'll just build a tree intermediate and throw it away. But our numbers need to be reversed. All right. Does that make sense? So can't see it. Let me move some. Well, very annoying. If we run it now, we have our tree, and it looks like we have a right leaning. Right? We start on the right here with 4. It has nothing on the right, and left and left and left. Perfect. Now, let's make another tree, tree 2, and let's fold out our numbers, but let's shuffle them up. Let's randomize them. Can't even spell shuffle. And let's change our tree to reversed. Let's take our print. This will be tree 2, and then we will call this shuffled. All right, and now let's see if we get our shuffled up tree. It's hard to tell if it's shuffled because I didn't save shuffle off, so let's actually shuffle them and print them. Right, so define shuffled as the shuffling of these numbers. And we need to print this out, so we'll copy off our number. Shuffled, and we will change our print. So let's see if we see anything interesting here in our output. We've got our numbers 0 to 1. We build a tree out of it. It's right leaning. We reverse those, so it's left leaning. Right? Every number that gets added is actually less than the previous. We shuffle them up. Excellent. This looks shuffled. 0 is going to come in first, then 3, 2, 4, and 1. All right, 0 came in first. That means that everything, since we know our domain, everything's going to have to go to the right. 3 came in, and then to the right of that will have to be the 4. The 2 came in. That was to the left, and then eventually the 1 came in. That has to be to the left of the 2. So I think we are done here. We have created the basics and outline for a binary search tree. Right? We have our tree. It is a list of 3 items, left, value, and right. We can reach in and get the value, which we didn't actually need at this point, and we didn't check for empty value or children, but we have those when we need them in the next lesson. And when we add, we simply are adding into a tree that may be empty. That is just a new tree. Otherwise, it's a tree where we have a left, a value, and a right. If the value being added is less than, it goes to the left. Recursively call the left. This is why it's a recursive data structure. Otherwise, if it's greater, go to the right. And finally, if it's equal, then we don't allow duplicates, so we're just going to return the same node. Next, what we will work on is removals, searching, but also other traversal functions. So depth first search and binary first, or breadth first search. Depth first and breadth first search. So we will continue on with binary search trees in Racket. Thanks. Talk to you later. Bye.